Hi, this is Tor Lacey. In this lecture, you will learn how to apply some of what you learned about geologic structures and interpreting block diagrams to sorting out the chronological sequence of events that have happened over geologic time to create the geology we observe today. These are some of the learning objectives of this lecture. In order to interpret the geologic history of an area, we need to study the rocks. This requires identifying the rocks and their minerals, as well as the structure of the rocks. Geologists record their observations in notebooks and by making geologic maps. Geologic maps provide the foundation of studying the geology and the data needed for creating geologic cross-sections and block diagrams. These provide a three-dimensional perspective of what's happening beneath Earth's surface, which allows us to interpret the structure and see the relationships among the geologic bodies. In turn, we can interpret a fourth dimension, geologic time. Earth is 4.6 billion years old, which is truly an inconceivably long period of time for humans who only live about 2/1000% of that time. For about 90% of that time, there was no life on land. Think of that. Nothing green, nothing moving around. Around 400 million years ago, life moved on to land, and the world began to evolve into something more familiar to us. The main objective to this lesson is to learn how to interpret the geologic history of a given area by arranging the geologic units in their correct chronological sequence. This is known as relative dating. For example, arrange the following events so they are the correct chronological order relative to one another. Joe Biden becomes president, World War II, today, dinosaurs go extinct, America's independence. This does not require determining the exact time when something happened, the numerical age or date, but instead arranging events in their correct order relative to one another, or their relative age. This is done by using relative dating principles, such as cross-cutting relations or original horizontality, which are for the most part based on common sense. The principle of original horizontality recognizes that material deposited from a fluid, air, water, or melting ice, will form horizontal layers. Superposition describes that as a sequence of rock layers form, younger layers are always deposited atop older layers. In this photograph, strata D is oldest and A is youngest. If strata is no longer horizontal, then we know the rocks have been subjected to deformation. In some cases, the deformation can be so intense that strata has been folded over onto itself, and the principle of superposition no longer applies. The principle of cross-cutting relationships states that a rock unit or structure that cuts through another rock unit or structure is always younger. In other words, the cutter is always younger than what's being cut. The principle of inclusions observes that rock bodies or fragments contained within another rock must be older than the surrounding rock. Unconformities represent a gap in the geologic record between the rock above and below the unconformity. Unconformities happen when deposition of sediment stops or erosion removes rock before deposition resumes. This cycle may take tens of millions of years, removing tens of millions of years of the rock record, and therefore tens of millions of years of geologic time. Let's take a closer look at the three types of unconformities. This illustration summarizes how an angular unconformity could form. Strata is deformed, then eroded, removing rock and geologic time. After more time, sea levels rise, flooding the strata, allowing deposition to resume. Deposition happens in water. The cliff in the photograph could be thought of as step 4. After sea levels have dropped and/or tectonic uplift has happened, the strata and angular unconformity are exposed above sea level. Nonconformities separate sedimentary strata from crystalline rock, either igneous or metamorphic rock. Erosion exposes the crystalline rock. sea levels rise, and new, significantly younger strata is deposited atop the older, non-sedimentary rock. The photograph is of the Great Unconformity, with 1 billion years separating rhyolite below from the strata above. Disconformities separate older sedimentary strata from younger strata. They are different than angular unconformities in that the strata above and below the unconformity have the same dip. Consequently, these can be difficult to recognize in nature. We can use the principles of relative dating and unconformities to arrange the sequence of geologic events in geologic cross-sections and block diagrams. Can you arrange the geologic events shown here from oldest to youngest? Can you identify the unconformity and what type it is? This brings us to the end of this lecture. Thank you for listening.